This is the solution to the exam for 2014 question number 4. So this is to do with linear transformations from polynomials of degree 2 to vector space of vectors, two-dimensional vectors, where the mapping is given by t of a plus bx plus cx squared is equal to a plus b and a plus c. So part A, we need to determine t of x plus 3x squared. So from this you can see that a is equal to 0, b is equal to 1 and c is equal to 3. So we simply substitute for a, b and c into this expression. So we get t of x plus 3x squared is 0 plus 1, that's the a plus b, and then 0 plus 3 is the a plus c, which gives the two-dimensional vector 1, 3. For part 2, we want to determine two distinct vectors, p1 and p2, which are polynomials of degree 2, which map to 0. So we want t of p1 to be 0 and t of p2 to be 0, but p1 and p2 are not equal. For all linear transformations, 0 maps to 0. So if we take p1 as the 0 polynomial, then that maps to the 0 two-dimensional vector. Then looking at a plus b and a plus c, you can see that this a plus b is 0 if a is minus b, and a plus c is 0 if a is minus c. So if we simply let a equal 1, then you can see that b is minus 1 and c is minus 1 will give us the 0 vector. So here are the two polynomials which map, both of these map to 0 and they are distinct. For part B, we want to prove that this mapping t of a plus bx plus cx squared is a plus b and a plus c. We want to prove that this is indeed a linear transformation. So we're trying to prove that t of alpha p1 plus p2 is alpha t of p1 plus t of p2. That's what we need to prove that t is a linear transformation. So we take two general polynomials in P2R. So we take a plus bx plus cx squared is polynomial P1, and d plus ex plus fx squared is polynomial P2, and we take alpha is a real number. So t of alpha P1 plus P2 is equal to t, so we just simply substitute for P1 and P2, and then we perform polynomial scalar multiplication here and polynomial addition to get this new polynomial. Then we apply the mapping t onto this polynomial to get this two-dimensional vector. All we do then is we split this two-dimensional vector and show it's equal to alpha times this vector plus this vector, which is equal to alpha t of p1, so this is t of p1, and this second vector is t of p2. So therefore we've proven that t of alpha p1 plus p2 is the same as alpha t of p1 plus t of p2. So therefore the conclusion is t is indeed a linear transformation. And that concludes the solutions to question number 4.